All right, so let's continue here with our discussion of aldehydes and ketones. We kind of previewed last class period what these reactions are going to look like here, all based on that electrophilic carbonyl carbon, right? So that carbonyl carbon is a really good electrophile because it lacks electron density because it's in that polar bond with oxygen. It also can accept a pair of electrons really easily because it's got that built-in leaving group, pair of electrons, that pi bond that can break. That pair of electrons can go on to that oxygen. And it's also just very accessible because of that trigonal planar geometry, all right? So that leads us to our reactions of aldehydes and ketones, what are called nucleophilic addition reactions. We're going to have, we've seen this before, so let's just kind of keep it in mind. We have our basic condition nucleophiles. Right, meaning no strong base acids are allowed. All right, we said a simple way to sort of spy that we got a strong acid that we want to avoid. So we're going to avoid positively charged intermediates. All right, in our mechanisms, we're going to need to do some proton transfers. So if we need a base, we can use a strong base. That's perfectly fine. But if we need an acid, it's going to have to be a neutral proton donor. So for example, water. Or oftentimes in your reaction mixture, it's better to just have the protonated version of your nucleophile present. All right, we'll see some examples here. Okay, if instead we had these nucleophiles that react under acidic conditions, we better have no strong bases. All right, so then we're going to avoid negatively charged intermediates. All right, we did have an exception. There are a few common anions that are compatible with acidic conditions, and those are our halide ions. Chloride, bromide, and iodide. Hydrochloric acid is a strong acid, and yet there are chloride ions floating around. It turns out that these particular anions are just really crappy bases, right? So they are compatible with acidic conditions. So if we need an acid, then great, we can use our strong acid. All right, but if we need a base, we're going to need to use a neutral proton acceptor. Water would be a good example, or again, even a protonated nucleophile. As long as it has a lone pair of electrons, it can accept yet another proton. All right, so let's see if we can't do some examples here figure out what our nucleophilic addition products are going to be. All right, so let's get an aldehyde or a ketone. All right, which one do I have here? An aldehyde, and we're going to react this thing with hydroxide. All right, so what do we have an example of? An acidic or basic nucleophile here? Basic nucleophile. All right, and we're going to reason through our mechanism here to see if we can't figure out what our product's going to be. I want you all to take a second to see if you can't tell me what our product, start off our mechanism here. What do we know? What's our nucleophile? What's our electrophile? Just give it a shot. No wrong answers, right? With these mechanisms, it's a good idea to just start messing with stuff on pencil and paper. It's not always that you're going to know exactly what to do before you even start. You want to get comfortable kind of reasoning through it, right? Going through and saying, all right, well, here's something with a lot of electron density. Let's react that with something that doesn't have a lot of electron density, all right? See if we can't understand these mechanisms, not just memorize them. My nucleophile is my hydroxide. And my electrophilic carbonyl carbon is my electrophile. All right, so let's have our nucleophile attack our electrophile. Right, again, we can't just do that one arrow. We got to have that built-in leaving group pair of electrons shown here. We don't want our carbonyl carbon to have a broken octet rule. All right, so if we draw our intermediate here, we got an alkoxide ion. As well as that hydroxyl group, okay? Remember, we said that our aldehydes and ketones, one of the reasons that this is such a good electrophile is it's really accessible because of that trigonal planar geometry. Well, whenever a carbonyl carbon gets attacked by a nucleophile, now it's got 4 bonds associated with it. So it's not going to be a trigonal planar, but rather a tetrahedral intermediate. And we're going to see these a bunch in this particular unit, so we're going to name this. All right, and whenever we get our tetrahedral intermediate, we're going to get in this habit early on of asking ourselves, is there a good leaving group? All right, and in this particular chapter, the answer is going to be no. Okay, we have these two. You're not kicking off this oxide ion here with its -2 charge. That would be ridiculous. If you just kick this thing off, we're right back to where we were. We got a carbon over here. That's an absolutely terrible leaving group. There's actually one. What's my 4th bond on this carbon here? Right, so remember, we have this aldehyde hydrogen here. I didn't bother to draw it in, but I can. Boom. which is also a terrible leaving group, right? So we don't have any good leaving groups here, so we're just kind of stuck in this alkoxide ion. What we're going to do now is one last proton transfer step. Notice this is a very similar intermediate to what we saw in our Grignard reactions. Your Grignard reactions, you have that follow-up step of that acidic workup. Here we're just going to have in our reaction mixture a proton donor. If I'm going to use this basic nucleophile hydroxide, what's going to have to be my proton donor in this reaction? Water. Right? I can't use hydronium or some strong acid. That's not compatible with these reaction conditions. Like we said, we're going to need to use a neutral proton donor. So the protonated form of our nucleophile is in this case just water. All right? And so that's our last step here. We're stuck at our tetrahedral intermediate. All right, so everybody take a second. Finish off our reaction here. That pair of electrons is going to reach out and grab that proton, giving us this product here. All right, so aldehydes and ketones will actually react with water under acidic or basic conditions and form these what are called gem diols. All right, these reactions are always in equilibrium in any aqueous solution of aldehyde or ketone, but that equilibrium does tend to favor the aldehyde or ketone form, right? That's not to say that we can ignore it entirely because this reaction is always taking place, but we will note that our equilibrium does lie in favor of our aldehyde or ketone, except for like the very tiniest aldehyde like formaldehyde. For the most part, these equilibrium again lie in favor of your aldehyde or ketone, but nonetheless, these reactions still occur. All right, so notice that in our nucleophilic addition reaction of our aldehydes and ketones, our carbonyl oxygen becomes a hydroxyl group because that carbonyl carbon gets attacked by whatever that nucleophile is. All right, and we're going to play this game with just a bunch of different nucleophiles. We made a master list of a bunch of different nucleophiles, right? We could take any of them and react them with our aldehyde or ketone, and we would get a similar process. Let's do another one here. All right, we'll take acetone. And we're going to react it with HCl. Would this be acidic or basic conditions? This is now acidic conditions. Okay, and if we try to play the same game that we just played before, say, all right, let's have our nucleophile attack our electrophile. We would get this intermediate here. All right, and ignoring how ridiculous this chlorine looks with its two bonds and its positive charge. What's wrong with this one over here? Can't have a negative charge. We can't have a strong base like an alkoxide ion under acidic conditions, right? So what did we do last time to manage our charges and make sure that we avoid these intermediates we're not allowed to have? Proton transfer steps. Yeah, protonation, right? So everybody take a second. See if you can't do this mechanism correctly, avoiding those intermediates, those negatively charged, whoop, I want that negatively charged intermediate. In this case, my neutral nucleophile here is itself a strong acid. So that can protonate that carbonyl oxygen. And now my chloride ion can go ahead and attack. Leaving me with my product, again, we see that our carbonyl oxygen becomes a hydroxyl group when our nucleophile gets added on to what was formerly that carbonyl carbon. All right, so we can just note here, we said that we can use a strong acid. In the case of our hydrohalogens, they are themselves a strong acid. There are a lot of other neutral nucleophiles out there. Water, alcohols, they are not themselves strong acids, so they wouldn't be able to protonate a carbonyl group, and instead you would have to have some sort of an acid catalyst like hydronium in there instead. Right? Typically you would dump in a bunch of strong sulfuric acid, which would create hydronium in solution and allow that to be your proton donor. All right, but you need a strong acid to protonate that carbonyl oxygen so you avoid any negatively charged intermediates. Cool. All right, so then let's just make sure we got this down. We don't have to do the full thing here. You can just give me products. so we're going to add that nucleophile to that what's now formerly carbonyl carbon. Our carbonyl oxygen turns into a hydroxyl group. All right. And I'm going to be good and show that it is my carbon and not my nitrogen that is bound to that carbonyl carbon. All right, if I take benzaldehyde, an aldehyde, and react it with this hydrogen sulfide, this is a neutral nucleophile. So when I draw my product here, I'm going to have to be good and remember to remove a hydrogen. So I now have that sulfur and that oxygen bound to that same carbon. All right, so we just want to remind ourselves that for neutral nucleophiles, they lose a hydrogen. Cool. So we take a nucleophile, we react it with an aldehyde or ketone. We can do so under either acidic or basic conditions. And we're going to get a nucleophilic addition to our carbonyl carbon, right? That electrophilic carbonyl carbon. All right, let's start talking about some sort of more special cases here. All right. Aldehydes and ketones. And alcohols. All right, so let's get a ketone here. All right, if I were to mix in this ketone with some methanol, everybody take a second and draw me the product that you would expect using this neutral nucleophile. My carbonyl oxygen becomes a hydroxyl group. My neutral nucleophile, importantly, it's my oxygen. That's my actual nucleophilic site here, so that's what's going to be attached. And it loses a hydrogen. All right, and this does indeed form. This is what's called a hemiacetal. All right, but it doesn't stop there. It will react with yet another molecule of this methanol, of your alcohol. All right, replacing that hydroxyl oxygen altogether. So now we got these two methoxy groups on there. And this is what's called an acetal. All right, so aldehydes and ketones will react with two equivalents of alcohols to form acetals. This reaction is particularly important in biochemistry. It turns out that this is how your body packages sugars together into starches that then it stores for long term in the cell. All right, it creates these acetyl bonds here. Cool. All right, the next one that we want to look at are our aldehydes and ketones. With that cyanide ion. All right, we had that example here. All right, and this is indeed the reaction that takes place. I'm going to draw out my nitrile group here. Be good and do my geometry correct as well. It's got that linear structure about that carbon. All right, so this part, nothing new. Okay, but we can take this product, and there's two common follow-up reactions that we can do. We can either treat it with our reducing agent, lithium aluminum hydride. All right, so that cyanide, that nitrile group can be reduced. Right? Remember, we can reduce aldehydes and ketones using lithium aluminum hydride. We can also reduce nitriles to amines. All right, so my extra carbon here, remember when we added that cyanide ion, we added an extra carbon, so that appears here. So now I have this 1-2 carbon spacing between what was formerly my carbonyl carbon with its hydroxyl group and my new carbon with its nitrile, with its amine group. All right, so we can reduce that nitrile group or we can oxidize it. It turns out that they're fairly easily oxidized with just acid and they would be oxidized to, again, I have an extra carbon, carboxylic acid. In my opinion, this is a very weird place to put these two reactions in this aldehyde and ketone chapter, but this is where they decided to stick them here. They say, oh, look, you can use cyanide as a nucleophile like we've been doing all along. Oh, and hey, by the way, there's these two follow-up reactions you can do as well. You can reduce a nitrile group, that carbon-nitrogen triple bond, to an amine group, or you can oxidize it to a carboxylic acid group. All right, and then the last category of kind of weird ones are now nitrogen nucleophiles. All right, nitrogen nucleophiles are kind of the weird ones when we're talking about our reactions with aldehydes and ketones. Most of our nucleophiles are very straightforward. We get this add-on of our nucleophile and our carbonyl oxygen becomes a hydroxyl group. That's this common theme we've seen over and over and over again, regardless of what nucleophile we chose. Yeah, we got to pay attention to whether it's acidic or basic conditions, but we don't really have anything all that much to consider outside of our mechanism, right? Unlike epoxides where we got a different product whether it was acidic or basic conditions. That's not the case here. All it's going to do is influence the intermediates that we see in our reaction mechanism. Okay? So up until now, our nucleophiles have kind of been doing the same thing over and over and over again. Our nitrogen nucleophiles are going to behave a little bit differently. We're going to have to break the world of nitrogen nucleophiles up into two different camps here. We're going to look first at primary amines. And ammonia, the very simplest amine. Well, technically not an amine because there's no carbons, but nonetheless, behaves the same. All right, so a primary amine, for example, is when that nitrogen is just bound to a single carbon. And ammonia is, of course, NH3. All right, so let's look at how these behave with our aldehydes and ketones. All right, so the first sort of weird thing that we're going to see with these nitrogen nucleophiles is they react not under acidic or basic conditions, but a third category we're going to call neutral conditions. Where we're going to see both positive and negatively charged intermediates. All right, calling it neutral is a little bit of a lie. When you do these reactions, you have it at slightly acidic conditions. Your pH is around 5. Right, but still pretty much in that neutral range. And again, the reason why we're having this distinction of neutral conditions is because we're going to see both positively charged and negatively charged intermediates in our reaction mechanism. All right, so let's go for it here. We're going to take our ketone. All right, we're going to react it with a primary amine. Okay, so this first step in this mechanism is going to be a nucleophilic attack of that electrophilic carbonyl carbon. All right, so everybody take a second and show me what my the product of this first step here. What is going to be my intermediate here? So I want to be good and show that my nitrogen is what's bound to that carbonyl carbon. My oxygen has accepted that extra pair of electrons, so it has that negative charge. What else am I missing here, though? Positive charge. Now my nitrogen, having donated that pair of electrons, now has 4 bonds, so it has this positive charge. So right off the bat, we see that we've broken our acidic and basic conditions rule, right? So that's why we had to say that we have this new set of conditions here, our neutral conditions, because this allows for both positive and negative intermediates, and we see that here. All right. Does this thing look like it's nice and stable and happy? No, we got mixed charges in here, which is always an unstable thing. This thing has too few hydrogens. This thing has too many hydrogens. All right, so you'll see this broken up in 2 steps in certain textbooks. We're going to do this the lazy man's way and do this all in 1 step here. We're going to show our oxygen grabbing this proton away from that nitrogen, right? So we got this internal proton transfer step occurring. So far we see something weird in our conditions. Our intermediate has this positive and negative charge, but if we look at our product here, this is basically exactly what we would expect based on everything we've been doing up until now, right? We have our carbonyl oxygen becoming a hydroxyl group and a nucleophile attached to that formerly carbonyl carbon, right? This is what we would expect our product to be. Okay, this is what's called a carbonyl amine. Okay, again, this is our expected product. But it turns out that these carbonyl amines are unstable. And this thing will continue to react here. All right. What we're going to see is this oxygen is going to get kicked off here in this process. But in order for it to be a good leaving group, what are we going to have to do to it? We're going to protonate it, all right? So what's going to happen is we're going to kick off this oxygen, or the nitrogen is. We'll see that here in a second. All right, but let's first protonate that oxygen so we have a good leaving group. This is where our slightly acidic conditions come in here. We got a little bit of hydronium floating around to protonate that oxygen. Right, so now my oxygen is a good leaving group because it will leave as a neutral water molecule. But what's going to kick that oxygen off, right? It's not just going to fall off all by itself. There's got to be this kick, this little impetus that pushes it off. And where that comes from is probably the most surprising part of this whole mechanism. It's that pair of electrons on that nitrogen that's going to come back down and kick off that oxygen. All right, so now we have this carbon-nitrogen double bond. All right, my nitrogen here is still protonated. So the very last step here is to remove that proton. All right, I'm going to need some base to do it. Since we're in slightly acidic conditions, use water. All right? And so here is our product of our reaction. We've gone from having this carbon-oxygen double bond to now a carbon-nitrogen double bond, what we call an imine with an I. All right, so our carbonyl groups, our aldehydes and ketones, will react with primary amines and ammonia to form imines. All right, so just to kind of summarize here, without all the steps in our mechanism. I'm going to do generic primary amine. So it's got this R group on there. All right, we've replaced that carbon-oxygen double bond with a carbon-nitrogen double bond. Again, what we call an imine. All right, and we want to note that this is for primary or ammonia. If it's ammonia, what's that R going to represent? Hydrogen, right? That would be our simplest imine that we could get. All right, cool. And we're going to distinguish this between what happens for secondary amines. All right, and amines are kind of weird in our classification system because that nitrogen can have up to 3 bonds. So by a secondary amine, we don't mean that the nitrogen is bound to a secondary carbon. We mean that the nitrogen itself is bound to 2 carbons. All right, so this would be an example of a secondary amine. Again, that nitrogen is bound to 2 carbons. And we're going to see that these react a little bit differently than primary amines with our aldehydes and ketones. Okay, we're going to show it the long way using the mechanism, so we'll save that for next class period.